Hello guys, KNOCKCAT this side. So let's solve today's GFG PUTD, that is strictly increasing array. So I hope you have already read the problem and at least give a try by yourself. So the problem says, given an array nums of n positive integers and we have to find the minimum number of operations required to modify the array such that array elements are strictly increasing. Changing a number to greater or lesser than original number is counted as one operation. So the problem is actually saying by applying some operations which is actually modifying some value, like changing this a to some a1 or like having some b to change with some b1, and we need to make sure that our array should be termed as strictly increasing. That is, this a is less than b, less than c, less than d, and there should not be any equality such that b cannot equals to c because this is not strictly increasing. So we have to apply operations, the minimum operation, such that we can formulate a subsequence, not subsequence, an array which is strictly increasing. So let's look at the example test case. So given that 1, 2, 3, 4, 5, 6, 4, we can have actually have taken this 6 as 4 because now 3 and 5 and we can have 4 here, and this is strictly increasing, and for this 5 I have made this as 6. So this would have turned this to an strictly increasing. Similarly, here we have 1, 1, 1, 1. So it makes sure that since all values are equal, we have to modify three values. So they have actually modified them as -2, -1, 0, and 1 remains as it is. But we can also make it as 1, 2, 3, and 4. Until and unless it's following the condition that we have to make strictly increasing, the number of operations they are also taking is 3, and this case will also take 3. So we can actually apply this operation. So now the point is how we actually think of this problem. So like since we need to maintain and strictly increasing subsequence, can I think in that direction only? We have to maintain strictly increasing. So can I think in a way that what is the maximum increasing subsequence I have already within myself? So if I look this case again, we have 1, 2, 3, 6, 5, and 4. So and strictly increasing subsequence, I'm saying subsequence. A subsequence can be any number of elements until it follows the same order. That means I can take 1 with 5 because they are following an order 1 by 4. Like 1 and 3 I can take. I can take 1, 2, and then I can take 4. So like order, subsequence. Can I, what is the maximum subsequence I can get, which is also increasing? So let form. So if I say 1, 2 would be a increasing subsequence of length 2. Similarly, 1, 2, 3 would be an increasing subsequence of length 3. And we can also see 1, 2, 3, 6. 1, 2, 3, and 6 is an increasing subsequence of length 4. And I think this is the maximum we can get. We can also have 1, 2, 3, and 5, which is of also 4. So now if I have taken this 1, 2, 3, and 5, 1, 2, 3, and 5 as maximum number of subsequence, which make us think that means if 4 is already in increasing subsequence, then the remaining elements are the ones which are actually violating the property. That means if I have 6 elements and 4 is already in strictly increasing subsequence, the elements which I am remaining with would be 2, and 2 would be the, and we can see 2 is the output here. That means 2 elements are violating. But now also like this case, that if we have 1, 2, 3, and 5 as a subsequence, that means we take 1, 2, 3, 5. We didn't take this element, and the next we have also an element which is also not satisfying. Now actually if I take 1, 2, 3, 5, in there between it is 6. In there between it is 6. That means I have to modify this element. I have to modify this element, and if I have to if I have to make this element increasing subsequence in this given, or like in the subsequence which I have chosen, so this value should be in a range that is between these two bounds. It has to be between these two bounds. Are you getting it? Because now if I'm taking an increasing subsequence and in between, I have to actually figure out what would be the best possible way in which I can actually accommodate those values which are not fulfilling the criteria of increasing subsequence. I should have put the values that comes between these two fixed bounds. And we can clearly see between these two fixed bounds, the only possible value that can reside and can actually form an increasing subsequence is only 4. We cannot have any value better than that. So that means 4. And yes, we can put 4 and 5. Since after 5 we can put any value, so I can actually put, yes, we can put actually 6 here, or any value greater than 5. So what I want to relate this, yes, the problem boils down to this, that yes, I can actually make this subsequence as increasing one, but if I am taking two values between which there is a subsequence or subarray which is actually not fulfilling. Because if I am, let's say, if I would have taken some values a and up to b, and I know a and b, a is actually less than b, that means a and b is following my property of increasing subsequence. It has to be increasing, strictly increasing. Okay, but then there are three values in between. So if I have this a and b in my subsequence, these would have fixed bounds. Let's say this is 5 and this was 7. Because if I have chosen 5 and I have chosen 7, I know the values at these points. So let's say these are 5 and 7, and now I have three values in between. I have three values to fulfill in between. So can I actually put three values in between 5 and 7 so that they have also turned out to be an increasing subsequence? That's the problem. If we solve, we will actually be very close to the problem. So 5, 7. These are fixed bounds, and the values we have to fulfill in between is 3. So let's put 6 first, because the only possible values are 6. And now any value if I put, that will not result in an increasing subsequence. Now, if any value I put, it will not result, because if I put 7, then 7, 7 do not follow. If I have put 8, then 5, 6, 8 would be one sequence, but then this dash and 7 would be a different one, because I have taken 8. Now this 8 is actually bigger than 7. So it's very sure that 8, this is forming decreasing one. So I think this thing is clear. So that means if I'm fixing two bounds, that if I am taking one value here and I am following some sequence to be followed with it in the later half, then the number of indices in between them, these two bounds, which are actually not following the LIS condition, should be, I should have enough values between them so that I can accommodate them. But here in 5 and 7 case, I have not enough values so that I can accommodate some values between them. So that means we can actually check which time I can actually consider some elements to be followed with B. Like some index I should be followed with J. I can only follow some index I followed with J if I have enough elements to accommodate between them. So now let's see here. I have 5 and 7 here. Let's say it was index 0, and this was index 1, this was index 2, this was index 3, and this was index 4. And the number of elements I need to accommodate, I can actually calculate from 4 minus 0 minus 1, that is actually 3. That means three values I have to accommodate in between. Now 7 minus 5 is actually 2. 7 minus 5 is actually 2, which is lesser than the values I need. Which is lesser than the values I need. Ideally, in order to fulfill or fulfill for those values, it should be greater than, the difference should be greater than my required values, because actually let's say this was not 7, this was 9. Then we have 9 minus 5, we would have 4. 4, and the values we needed here was 3. So this would be an ideal case, because now I would have put 6 here, 7 here, 8 here, and I have 9 here. This is a minimum. So at least I would have 4. At least the difference should be 4 in order to fulfill this 5 and 9 between, because in between, if I have three elements, I should have at least 4. if I need to fulfill three elements, the difference between those two fixed bounds should be this requirement plus one. Why? One difference is between them, one is between them, one is between them, and one is between them. We need four variations, that if we need to fix three elements, four increasing subsequence would be like forming here. So if I had to actually consider, so now the case is like, yes, we would think of a fashion in increasing subsequence because that would be more optimal to think that how can I get an increasing subsequence. But if I am taking this I and some j has to be followed with it, then I have to also accommodate these values because these ij I am taking, but the values between them should be actually somehow which fixes, which comes under those I and j and also be an increasing subsequence. So for this, the number of elements would be j minus I minus 1, and the difference should be at least the difference should be this plus 1. It has to be. So the same thing I've written. The requirement was the difference has to be requirement plus 1. So can I think this can help, like what I'm saying? So actually, this can help us solve this problem. How we formulate the longest increasing subsequence to our conditions satisfaction. So now let's look for an example test case. Let's say we have 1, we have 2, we have 3, and now I have, let's say, 2, 1, and I have 5, and I have, let's say, 6, and I have 9. So now the maximum subsequence if we can form was 1, 2, 3, 5, 6, 9. 1, 2, 3, 5, 6, 9. But when I have to follow 3 with this 5, 3 with this 5, so the values between these 3 and 5 should accommodate. So we would actually check, are these values are accommodating, that this is 3 and this is 5. So the values I can actually, the difference I'm getting is 2, and the values that I need to fulfill are also 2. And I clearly said above that it has to be greater than the number of values I am feeding. So that means I cannot take this 5. That means I cannot take this 5. So I will look this 3 now to bound with 6. So I will check 3 to bound with 6. So 6 minus 3 is actually getting 3. And now the number of elements that we need to accommodate between them would be 1, 2, and 3. And I am getting 3. 3 is not enough. It has to be greater. It has to be greater because 3, I would have kept 4 here. I could have kept 4 here. I could have kept 5 here. I would have kept 6. But it should be 7. If it had 7, I would have got 4. So it has to be plus 1 because now 6 and 6 don't follow. So now I would have thought of 3 to combine with 9 in the longest subsequence because I need to fulfill that the bounds, like the values which are inside those bounds, will also follow the condition. So 3 and 9, the difference we are getting now is 6, and the elements we have to accommodate is 1, 2, 3, and 4. And since it is greater than 4, that means we can actually formulate some values between them that satisfy the condition. So we have kept this 4, we have kept this 5, this 6, this 7. So now this is following an increasing subsequence. So that means I can actually take 1, 2, 3, and 9. 1, 2, 3, and 9. So this is a maximum subsequence I am getting. And that means the number of elements that do not satisfy the condition was actually n minus this maximum subsequence, because now this subsequence has formed such that the values which are not the part of the subsequence will also be accommodated if I take elements in this fashion. Because we see when I take 9, between elements 3 and the elements between 3 and 9 are also have followed the sequence of increasing subsequence. So it means if I can formulate increasing subsequence in a fashion that fixing two bounds, the elements between them would also be an increasing subsequence somehow, then I can actually formulate my increasing subsequence with this. But if beside with increasing subsequence, this condition is not satisfying, then I cannot add that as my subsequence. So this is a problem. And now let's think of how we will actually solve the problem. So let's take this. So we will think in a recursive way. So like the first case, like if I had to add this element to my subsequence, so I would say that either I can take this element and I cannot take this element. Either I can take this element and I cannot take this element. So since we have, let's say, some index I and we have some previous index pi. Why? Because when I have to take this j, I would be actually checking this I, that these two are following the condition. So for taking this element, I should be knowing what I have taken previously, because then only I would able to take the difference and would check that condition. So that means I come up with this. So now this element I can actually take in my subsequence or I cannot take. So let's take the not take case first. So I would say, okay, I am not taking this case. That means the answer that would be added would be 0. And I would have called this function, but this time I would have called that function with I plus 1. And since I am not taking this function, the previous I have would be the same. That's it. And now I would say this time if I would take this element. So currently when I am at when I am calling my call from 0 and minus 1 means I have not considered any case. I have not considered any case. So I would have checked, okay, for take case, like if I have not taken anything till now, if I have not taken anything till now, that is my previous minus 1, I have not taken this I is also have not been taken till now, or either I'm not taken, or the condition that we discussed, that firstly nums of I has to be greater than my num of priv num of I has to be greater than priv, and then the difference condition. Okay, I'm not writing fully here, that difference condition, that j minus I, the number of element that we need to fix element, should be actually less than that the difference we are getting, or we can say the difference has to be greater than the number of elements we needed. So, and this time if I, that means now I am taking this element. So if previous minus 1, so I can actually take this time I would be adding to my answer, and I would be calling a function to index plus 1, that I will say now go to next index, but this time since I have already taken this as priv, because if I have not taken, I am taking this time. So that means this index was my previous for next one. Okay, this index was my previous for next one, or if that condition follows, then also if this one something was already priv, and then I would checking, okay, if this follows, now next time my priv would be this I, because now I, when I have taken this j, so next time when I would be at j2, this j would be my priv. So I will move to another index with this index now my as priv, and since it will add to my answer, I did 1 plus, and then I can say the max of the length would be like the max of the take case and the not take case. Okay, that's it. So like 1 2 3 5 5 6 7 10. Let's look like how the recursive tree will be look like. 5 5 was 1 2 3 5 5 5 6 6 7 10. 5 6 6 7 and 10. Okay, that means I started my call with 0 and minus 1, and I have nothing. I have nothing. So first I can say, okay, I am not taking. That means I move to index 1 without taking something, not take case. And when I'm taking, I say yes, this time my priv, I actually take, come to index 1, and the previous I have taken, these are indexes, I have taken 0. The previous element I was taken as 0. Now, this was like, okay, I didn't start it with 1. Now I want, so this was like empty, this was, I am taking an empty subsequence. And this was, I have taken 1 as in my subsequence. Now, this will say, okay, I have not taken anything. So this time again, I am not taking. I will come to index 2 with minus 1. But this will say, now I am thinking to taking 2. So I will say, okay, I am taking 2. So I will move to index 1. And since I have taken 2, the previous index was 1. Okay, that means I have, now I am taking. So 1 would be my answer. And the element that I have taken is 2. So I am taking 2 in this subsequence. This one. This will say, okay, I am not taking this time. That means I came to index 2 with the previous that only, this previous only. And this says, I am thinking to take, but if I have to take, the condition should satisfy. That is, it has to be greater than. And the difference of 3 minus 2 would be 1. And the element that we need would be 2 minus 1, that is 0. And 1 is greater than 0. So actually we can take, yes, I can come to index 2, and now the previous I would be taking as well. And similarly, later on, the maximum answer, this would be, and now the subsequence would be 1 comma 2. And similarly, the maximum subsequence that we can form, taking care of this condition, would be a maximum sequence following the condition, and the number of elements that will not follow would be n minus, let's say, longest increasing subsequence, which is not longest, let's say longest increasing subsequence star, because it has some addition condition to it. So this is how we will solve this problem. So recursively, when I did here, this is the same thing, but this will give us a TLE. So I would have actually but the base case would be like when my index came to n, that means I am at the end and I can just return 0. And since we will memoize this because there would be overlapping subproblems, I would have actually checked for a case that if dp of my index, my priv plus 1 was already fulfilled, then I can return this. And here I was storing onto same on my dp. This will show that, and I will show this in my code. So let's move to the code editor. So let's come to the code part. So first let's have a variable name as for the array size, and we know the number of total elements I have minus the maximum sequence I would be getting would be the number of operations. So 0, the starting index, minus 1 that I have not taken anything till now, and nums. Let's make this helper function now. Integer helper. It would be integer index, integer priv, vector of int and of nums. And if base case would be if my index reaches to the num dot size, that is to the very end, I can actually say return 0. Now, if let's say first case would be not take. Not take would be like helper of index plus 1, and that means I'm not taking that case, so priv remains same and nums. Now let's say that take case actually 0, and the take case is if my priv is equals to minus 1, that is I have not taken anything till now, or nums nums of index is greater than nums of priv. Okay, and only greater element is not the condition. The difference, like if I have fixing these two bounds, the number of elements I should be able to accommodate, that is in the range. So the difference, their difference should be greater than the number of elements I have to accommodate. And the number of elements I have to accommodate was index minus priv minus 1. So it should follow at the difference should be greater than the number of index priv. So if that's the case, I can say, okay, take is equals to max of 1 plus, because this will contribute to my answer, index plus 1. This time my priv would be index because now I have taken this element, nums, and the not take that I have already taken above. That means I am this time either I'm taking and the not take, that means I am still not taking. So, and then return take would be our answer because I have already done the max of here. So let's see. So we are getting 2. Hopefully it works fine. It will give us a TLE because now it would be having, so like we are getting a wrong answer in this. That means we have to return max of take, not comma not take. Let's check one more time that okay, priv equals to minus 1 if nums of index is greater than nums of priv, and at the same time the nums of index minus nums of priv should be greater than my index minus priv plus 1. If that's the case, take would be equals to max of 1 plus helper index plus 1. Index would be this nums and not take case. And why this maximum I have to return max of take, not take, because what if this condition didn't run? So like when I would be having 1, because what if when not take is actually yielding us higher result, when not take is actually yielding us higher result, and this condition cannot able to run because none of them follow. So that's why I have to take max of not take comma not take also, because again not take is coming with some answer, and this condition will only run if if the current I and j would be falling. So that's why. So max of this, and now we can see we are getting TLE. That means it has overlapping subproblems. So we have to memorize it with a DP. So let's make a DP array of n plus 1, vector of n plus 1 minus 1. Okay. So I can actually pass my DP array, and let's take this same snippet here, comma, and let's as a reference say is DP, and the function I have called here DP, and one I have called here DP. So since we are doing minus 1, and if I would have say the DP of index priv not equals to minus 1, and I would have said return DP of index priv. So priv is minus 1, and we know minus 1 index is not exist. So can we do a coordinate shift that minus 1 should represent with 0, and now 1 is representing 0 is representing with 1, 1 is representing with 2. We can do this like this. So minus 1 is not actually minus 1. We will represent minus 1 with index 0. So that's why I have taken n plus 1 dp. So now I can actually say priv plus 1, because minus 1 plus 1 I would have made it 0. So this, and here I will say okay, store this in dp of index and priv plus 1. So let's hope this will work fine. And 2, and okay, let's submit this. So this is like just LIS only, but with this condition we actually change that what the according to the requirement. So on the very beginning I thought of the same thing, but then I didn't thought of the condition. So but then I able to figure it out, and I solved this here. And this was when I actually figuring out top down, and the top down is pretty simple, but I was actually missing one case, and that I will deal here. So like how we will write top down. So like again, for top down we can actually do this in order of NDP, and let me tell you why. 1, and also since 1 would be our answer, because any subsequence if you start with 1 has to be your maximum subsequence, because 1 is already in sorted. And let's say integer maximum LIS as 1. I was actually initializing it with 0 in my prior cases that lead to wrong answers. So now okay, now let's say I go till n, okay, and j I am checking from till less than I. What I'm doing, I is iterating here only, and j is actually behind to I, behind like till less than I. So I am actually checking that if I can take j, if I can take something like this, like if my nums of I is greater than nums of j, okay, like nums of j is less than nums of I, or we can say nums of I is greater than nums of j. If this is a condition, I would say okay, tell me, I will ask j what is the maximum subsequence you are already forming. So let's say it has some formatting some dp of j, and the answer is already in dp of j. So the when I would add I, because I is following that condition, I would say okay, now dp my dp of I would be what, the value at dp of j plus 1, because I myself is adding to the subsequence. So the similar thing I would say the same condition, but this is we are doing with dp. Like this is quite intuitive also. Like I am saying I am taking for these two pairs. So is nums of I is greater than nums of j in this manner, because I is already standing from here and it is checking for the previous values, that if I am greater than you, can I actually form a subsequence with you. So if nums of I is greater than nums of j, and that same condition, that the difference of nums of I minus nums of j should be actually greater than I minus j minus 1, because now I is that, j is actually priv here minus 1. So I can say my dp of I would be max of my dp of I that I already have, and 1 plus dp of j. That's it. And I have to make it as max LIS as my max of max LIS comma dp of I. And now I can actually say return n minus my max of LIS, and max of LIS. Here we would not actually getting the answer at here, Because why we not get the answer at here? Let's say we are at DP array, and I said, okay, let make pair with this index. So I would have put this value here, and I would have moved at this 4. Let's say the subsequence till now is 4. Now this value, if this value cannot be able to form a pair with this, if this value cannot be able to form a pair with this will never be formulated to 5. This will never be able to formulate to 5. And what if I have not include this index, the maximum I am getting is 3, and this was 3. So in this case, I would never, or even if I take this, we are still getting 4, and let's say this was 5 now. Okay. Now this element cannot be bounded with this. This was 5, but like the DP value is 5 here, but this cannot formulate with this. So this would have not make it 6. But if I take this element, it has make 4 with this. So now DP of n would have containing 4, but the maximum we have till now is 5. So that's why we are taking the maximum in that DP array. And now we do return n minus max LIS, and okay, DP n was not declared in the scope. So let's declare a variable int n is equal to nums.size. Let's run this, and let's see. So we are getting 2. So now let me submit this first. Then I will tell you that what mistake I did there. And we have to, okay. So actually, let's say if I not initialize this as 1 and it was 1 already, okay. So then it will say I is less than 1 and j is 0 less than 0. Like if my n was 1, so it would run like 0 is less than 1, yes. And the second loop would have run 0 less than 0, which will never run. So my max LIS will never get updated. That means I would have make it to 1 already. And that was something I was not doing here. I put as it's 0 only, and I was figuring out what was actually getting wrong. Here I also like put the same thing because I thought it was some internal error, and that's why I'm not getting something. Here I was figure out, but I was in a hurry. I put it down, but I didn't update it as well. So, and then eventually this is the same piece of code that I've actually mentioned here, and this time limit actually that we showed, and that's why we solved this with over DP. Why we did a coordinate shift that I've already explained, and this is one. So let's come with this approach. The time complexity for this approach would be 2 raised to the power n, because at every point we have two choices, either to take, either to not take. Okay. So, and the space complexity, you can say 2 raised to the power n only, because these number of recursive calls would be stored in the stack. There is a recursion stack. So that's why it's not feasible. So now we come up with this approach. This is actually we tend to memorize the recursive calls which we have already calculated. So that's why we have made a n square DP for that. So order of n square are space complexity, and order of n recursion stack space, because at worst it's also storing n calls in my stack. And the time complexity for this also is also order of n square. In this approach, we are actually using a space of only order of n, and we have actually seen why, because we are formatting these two pairs on the same condition. There we was taking prevent index. This is actually same, but we realize that I can actually see I and j with this, and this can only be done in one DP array. There was we maintain two states. That's why we for maintaining those two states we have a 2D array. But here we can realize that yes, only one state can help us for forming the maximum. So that's why. So now the time complexity for this would be the best approach, I feel, would be the order of n square, and the space complexity for it would be order of n. So I tend to show you the mistakes so that because these mistakes cost when we actually setting in a contest. So like one should avoid them not being in a hurry at every time. So that's all about the code. We solve this problem using this. You get to learn LIS, but with star this special condition. Because if I have to formulate 4 and 8 and something have to accommodate between, then I have to look these two indices, how much they can actually offer. So that's all about the code, and I hope you get to learn. So thank you and knock at this side.